Hello everyone, so welcome back to this second lecture of this week. So we will now focus on the neural networks. So after having some initial idea about supervised machine learning, we will start talking about shallow neural networks in this lecture. So the topics we will cover in this lecture are shallow neural networks. We'll talk about universal approximation theorem and a little bit of nomenclature. So this is what we discussed in the last lecture. So we talked about this gradient descent technique in very shortly, that what happens, you have a loss curvature and then you start with some initial approximate parameters and then you go in the direction of the negative direction of your gradient, right, loss gradient. So that's what is called gradient descent, and then in that process you keep on obtaining better and better approximate of your parameters, and once your loss is very close to 0, you typically converge and you say this is my parameters that are frozen, and you do that using a gradient descent technique. Now we talked about just linear regression in the last lecture, but this is very limited, because that means you can only approximate a function that is a line, right. So now what about describing input output mapping that are not lines, and you may want multiple inputs, multiple outputs. So how do you typically handle this general case, right? And that's why we will, in this lecture we will talk about shallow neural networks, which are flexible enough by which you can describe any arbitrary complex input output mapping, right, and you can use as many inputs as you want, as many outputs as you want. Okay, so here's an example of a shallow neural network. So you can think about, let's say you have only one input and one output, and you have 3 neurons in the hidden layer, right. So I can visualize this using either this image or this image. Here I am explicitly showing the bias terms. So you are seeing the bias terms also here, and here the bias terms are not shown, right. So there are always some bias terms, right. So for example, and how do you describe this? So we will see that even a very complicated neural network also you can write it as an equation. This is a very fairly simple one. So you can write an equation for this. So you want, what is y? Y is a function of x and the parameters phi, parameters of the model phi. What are parameters? Let's see. So I need to get y. So I have phi naught, the bias term, plus phi 1 h1 plus phi 2 h2 plus phi 3 h3. So phi naught plus phi 1 h1 plus phi 2 h2 plus phi 3 h3. What is h1? H1 is again some nonlinearity over theta 1 0 plus theta 1 1 x, right, and so on for others. So if you see here, there are 1 2 3 4 5 6 parameters going from input to the hidden, and then going from hidden to the output there are again another 4 parameters. So there are 10 parameters here, right, in this network, including the bias terms. Okay. And what is the activation function we use? So we can use any nonlinear activation function, right. So here we will use ReLU as the default method, and it will help convey some very important points about shallow and deep neural networks. ReLU function is like very simple. I mean, so whenever the input is greater than 0, you retain the input as it is, right. So if it is equal to 0, retains the input. If it is less than 0, you just take the 0, right. So that's the ReLU function, right, but it will induce nonlinearity, and that's what we will require for shallow neural networks. And we will see why this nonlinearity is so crucial in approximating functions, right? So any arbitrary function you can approximate once you have some way of giving nonlinearity. That was not there in the linear regression. They're all lines. Okay. So this model, as we counted, has 10 parameters, and it's a family of functions, right? I mean, I can give so many different values of these 10 parameters, right? I mean, even if you say phi naught varies from 0.0 to 1 in a step size of 0.1, then also there will be huge number of values. So it's a family of functions, and one particular value of parameters will determine one particular function, right? And once you have these parameters, once you know the parameters, you can run the inference, right? And you have to have a training data, let's say I data points, and you can define a loss function, say least square loss, and you change parameters to minimize the loss. So whatever we learned in the last lecture holds true. That means that's generalizable across any model architecture. You have to redo the same things, get some data, define a loss function, minimize the loss function, update the parameters accordingly. Once your parameters are frozen, use that for inference, right? That are like standard across architectures. So fine. Now, given this shallow neural network, then what are the important things, right? So these are some particular example from this family, some particular equations, 3 different choices of parameters, right? So, and you see now, I mean, this is looking interestingly nonlinear, right? Just by one shallow neural network and just with 10 parameters. And you see there are 1, 2, 3, 4 regions, 1, 2, 3, 4 regions, 1, 2, 3, 4 regions. That is also interesting. There are 4 regions each. There are 4 regions, right? 4 linear regions, you can say, 4 linear regions in each of these, right? 4 linear regions. Okay, fine. So we will look more into that how do you determine what will be the shape of this final output given a particular shallow neural network, right? So let's break it into 2 parts. So we saw already that y is phi naught plus phi 1 h1 plus phi 2 h2 plus phi 3 h3, and h1, each h1 is nothing but it's like a regression, right? A simple 1D regression, but a nonlinearity imposed on that, right? So it's a linear regression and a nonlinearity, that is ReLU. That's all is each hidden unit. Input hidden is this, right? And then you just combine 3 such hidden units and add some offset. So linear combination of that plus an offset. That's all is the shallow neural network, right? So should not be very difficult to understand. So let's see. So we have 3 different linear equations. So theta 1 naught plus theta 1 1 x. Let's say one equation is like that for some choices of theta 1 0 and theta 1 1. So I can say, for example, theta 1 1 is greater than 0, slope is positive, and theta 1 0 is less than 0. The y offset is negative. Similarly, here theta 2 0, y offset is negative, and theta 2 1 is positive. The slope is positive. In the third one, though, the slope lift is negative and offset is quite positive, right? So you have some idea by seeing the equations. Fine. So you have 3 different lines, right? So all these 3 linear regressions are 3 different lines. Now, what actually happens when I apply the shallow neural network, right? In a shallow neural network. First thing I do, I have a nonlinearity imposed on that, right? So theta 1 0 plus theta 1 1 x is good, but then I have a nonlinearity ReLU. So what will ReLU do? All the negative things will go to 0. So you see now immediately this is no more a line, it's a nonlinear curve with 2 regions, right? So one region is 0, another region is having some positive slope. Similarly, here 2 regions, and here also 2 regions. So, immediately once I apply ReLU, I may get 2 regions. Yeah. So good. So, this is what will happen. So, you are going from X and you have reached H1, H2, H3, right. So, that is what we have done till now, H1, H2, H3. Now, what next? I have to now combine H1, H2, H3 to get Y, right. So, phi 1 H1, phi 2 H2, phi 3 H3 plus phi naught, right. That is how I will get Y. So that means first I have to see what happens if I multiply them and by some weights. Now, phi 1, phi 2, phi 3 are just scalars, so they can be positive, negative. So, like here, so this applying phi 1, you can immediately guess phi 1 is a negative weight, right. Then it's that is how this is, the direction has been changed. Here the same direction, so phi 2 is greater than 0. You can even guess if it is greater than 1 or so on. We don't need to. Similarly, phi 3 is also not changing direction, so greater than 0, right. Okay. So after multiplying with phi 1, phi 2, phi 3, you get another such outputs, right. We are looking them in a compact space, right, so that we can easily visualize this. Okay. Next what? Next comes the final sum, phi naught plus phi 1 H1 plus phi 2 H2 plus phi 3 H3. Now, this is what I saw in phi 1 H1, phi 2 H2, phi 3 H3, plus I will add a y offset phi naught, right. So, which of these 3 regions will start first? See, this is 0, but this is already doing something. So, this is what will start, and let us say my offset was, I think, some negative value here. So, I will just put it slightly down. So, I will start from here, right. That is what is happening. I start from here, Now, till when I can keep on going, right, as x increases, till when I can keep on going, till I receive the first join, we can call it a join. That will happen, you see this join comes first, then second and third. There are three places where the change will happen, right. So, I am going nicely like that until I achieve this point. What should happen there? Now, this would anyway keep on going down, but now you have a further down slope, right. So, it will further intensify and go down drastically, right, until it is at the second join, right. So, now I am at second join. So, yes, what should happen now? So, this is still going down and this is also going down. So, this is anyway continuing here, but something else has happened, this has gone up, right. So, it will pull it up, and depending on the value, let us say it is pulling it up like this. So, right, so pulling it up like this, it is going until this point. Now, what happens? So, others are going same direction, but this negative slope has gone away, right. So, that means some positive increase. So, it will further increase, right, it will further increase, and that is what you see, right. So, negative, more negative, became positive, even more positive, right. So, you get 4 different regions, 4 regions. In this way, by this simple shallow neural network that had 3 hidden neurons, right? You get 4 regions. So, and you can try out, I mean, you can see different values of phi naught, phi 1, phi 2, phi 3, etc. can give you different kind of things, but they would have 4 regions. They would have 4 regions. Yeah. So, this we can call it as, these are piecewise linear functions. So, they are linear, not completely linear, but piecewise linear functions, and you have one joint per ReLU function, right. So, there are 3 ReLU. So, there is a single line and you have 3 joints in between, right. So, 1, 2, 3. and the joints are at the same place everywhere. So yeah, so three joints. Right? Okay. Now, how do I depict a neural network? So this we saw earlier also. So you have the hidden. So in the shallow neural network, you just have one hidden layer. So you will have some neurons, say H1, H2, H3. Now each one is nothing but a linear regression followed by a nonlinearity, right? And that we are keeping it as ReLU. So theta 1 naught plus theta 1 1 x ReLU, theta 2 naught plus theta 2 1 x ReLU, and so on. So once you have this H1, H2, H3, the y, the final output can be written as phi naught plus phi 1 H1 plus phi 2 H2 plus phi 3 H3. So each parameter, this multiplies its source and adds it to the target is what is happening. Now, the idea of doing this analysis, right, what happens from linear regression to ReLU giving you one nonlinearity and then multiple joints, is that whatever function you take, like let us say this is my function that I want to approximate, you can always define this function using some piecewise linear functions, right. Like this is, if you are given only 5 linear regions, you could approximate it like this: 1, 2, 3, 4, 5 linear regions. If you were given a budget of 10 linear regions, you could do even better. This is with 10 linear regions. And if you were given a budget of 20 linear regions, you could have done even more better, like this is with 20 linear region. And this looks nearly very good fit, right. And what do you need for 20 linear regions? As we saw, I just need 19 ReLUs. That means I need my shallow neural network with 19 neurons. So 19 neurons in shallow neural network, and that's all. That will give me a good fit to this more complex looking function, right. And this is why, using a simple shallow neural network, you can describe any 1D function to an arbitrary accuracy, right, by allowing more and more linear regions. You can actually describe any function to an arbitrary accuracy, and this is what is also mentioned in the universal approximation theorem. So which gives you a formal proof that if you have enough hidden units, and we saw why that is important, if you have enough hidden units, a shallow neural network can describe any continuous function on a compact subset of some d-dimension data to an arbitrary precision, right. Yeah, I mean, why do you need compact subset? But because otherwise there will be infinitely many linear piecewise regions that you will need. So once you have a compact subset, yes, you know its range. It ranges from some start point, some end point, and then you can say whatever is my function, doesn't matter. I'll always describe it using some piecewise linear functions. I can just write some piecewise linear function that helps me approximate the overall thing, right. But if this was an infinite domain, was infinite, you could not have done that with finitely many neurons, right. So that is why you also mention on the compact subset of the real numbers. So you can, if you have a function in a compact subset, then you can always describe using a shallow neural network, yeah, with enough hidden units. And I hope you got this idea that the simple nonlinearity like ReLU, you can give one piecewise linear function per ReLU, right, and you can have increase the number of hidden units, and that will give you more linear regions to better approximate your function. Okay. Now your question may be fine, that looks good. I mean, I can have as many neurons as I want to describe an output, but what if I have more than one output? Let's say I want to predict 2 different outputs from given my input. Let's say freezing point and boiling point given some data, right. No problem. I mean, you can still use the same architecture, and you say, okay, rather than using the simply y, I'll use y1 and y2. So I have my h1 to h4, the 4 hidden neurons. y1 will be phi 1 naught plus phi 1 1 h1 and so on, and y2 will be phi 2 naught plus phi 2 1 h1 and so on. Now interestingly, see the 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 points of the joints will be determined solely by this h1 h2 h3 h4. So let's say you already know from the other joints, but your final outputs can be different, right? That will depend on these phi values. So this can be a one output, right? So you are still using the same joints, but the individual piecewise linear functions are different, and same with y2, the individual functions are different, joints are same. So two different arbitrary outputs can be described by using a shallow neural network, but using more than one output neurons. Okay. So in general, you can have arbitrary number of inputs, hidden units and outputs. Let's say you have d naught outputs, d hidden units and di inputs. So what you would do? So first of all, you have to have some way of describing the d hidden unit. So you say, okay, of the dth hidden unit is nothing but nonlinearity over theta d naught, the bias term, plus I is equal to 1 to di inputs theta di xi, right. So for taking input the xith input, so you can have d hidden units, and your output will be 1 to capital D, because there are capital D hidden units, phi j d h d, right, plus the y offset phi j naught, right. So like that you can describe with multiple outputs, hidden units and inputs. So like here you have 3 inputs, 3 hidden units and 2 outputs, right. So how many parameters will it have? So it's not very difficult to compute. Each hi will take 3 inputs and a bias. So there will be 4, right. Each hi will have 4 parameters, 4 into 3 for hi, plus now hi plus another bias, and this will feed to each output. So plus 4 into 2, right. So this will give you 20 parameters. So this particular network will have 20 parameters. Okay, and now coming to some nomenclature. So we talk about y offset, we call them the bias edge. The slopes are the weights. So all these are the weights. Now if everything in one layer, so you can call it the input layer, hidden layer and output layer. In everything in one layer is connected to everything in the next layer, or it's called a fully connected network. That's the default way deep neural networks are used. So a fully connected layer where all these are connected to each other. There are no loops, so it's a feed forward network. So always going forward, and after you apply ReLU, the values are called activations, and before applying ReLU, they are called pre-activations. So you will have pre-activations here, and you will have activations here. So these are HI are activations, and before you apply A, whatever is inside are called pre-activation. And if you are using a single hidden layer, it's a shallow neural network, and if you are using more than one hidden layer, it's a deep neural network, right. And typically number of hidden units that you have is the capacity of the network. Okay. So we started with talking about from regression. We started discussing from regression model that given an input of this format, how do I convert into a model output? And then we have built a model that can take an arbitrary number of inputs, right, and arbitrary number of outputs, and you can have any function of arbitrary complexity between the two, and you can still try to describe that using a simple shallow neural network, right. That's what we have achieved. Now question may be like, okay, fine, this already looks good. Now why do we need a deep neural network? Now that is what we will see in the next lecture. So for shallow neural network, you can go through chapter 3 of our UDL book. Okay. Thank you.